Hello! So, I think it's time to start. So, thank you very much for being here today because I was working a lot on this presentation. So, I hope that I can show you interesting things because, first of all, my idea about the DICE model, which tries to describe the macroeconomic influence and impact of climate change, would behave something like this. So, if macroeconomists in central bank or elsewhere are trying to model the economy, they are always using some kind of a DSGE model. So, it's a dynamic because it links different sectors of the economy all together, and that it tries to maintain an equilibrium like what you were able to see on macroeconomics. And it's stochastic because it's developing in time. So first of all, I would like to define DSGE models within 2 slides, so it will be not that much, just to see that what is the concept behind this kind of models, and then we will see how DICE models can be different. So can we consider them as an alternate version of this model? So yeah, they are used widely, but let's see. So in DSGE model, we are trying to define. So you remember on the first class and practically the entire international finance class, when I was always writing up this relationship between the main sectors like households, companies, and all the other actors. This is doing the same thing, just with equations. So we have household, we have 2 kinds of firms, so that's why this is sophisticated, because one is final good producing firm. So in this case, they are working in a competitive market. So that's why they are not able to achieve higher profit levels, but they are motivated to create higher productivity. But also we have another kind of firms which are in an oligopolistic state. So that's why they are able to set prices, and also they are operating completely differently in the level of productivity generation. And also we have a central bank which tries to balance all these things out and sets interest rates. And also you can see that we have no residents in this, and also the state is missing from the generic or default DSGE modeling, so practically we don't have any foreign exchange rate. So additional versions, they are build this thing in, but this is the baseline model. And after that, we can use this to analyze optimum monetary policy. So what should be the policy rate for the central bank? How this policy rate should affect these sectors? So central banks are absolutely using them. If you are looking on interest, so inflation expectations on the central bank websites, and you can see always this graphs, which right now we can see always that inflation is now increasing, but sooner or later it will decline, and there is also a confidence interval around it. These are always produced by DSGE models, so that's why they are heavily used. And yeah, this is the description of the DSGE model. So we can see that there is a demand side, aggregated demand, there is aggregated supply side, there are productivity shocks, there are demand shocks, there are markup shocks, so, and also policy shocks from the side of the monetary policy. And mostly the art here, because writing up the equations are quite similar and quite the same what you are able to learn on macroeconomics. Here the art is the parametrization. So what kind of initial parameters are you using, and how can you fit it to real life data? Most of the articles are writing about this thing. So this is where you have to define the entire model. But the problem is The DICE model is way narrower than this. So if we are opening, or if we are starting the presentation at the beginning, then we can see that DICE model is focusing only on one thing, that what should be the optimal tax ratio or pricing or something like this. So let's say tax on carbon emission. Because there is a theoretical social cost on carbon emission, because sooner or later carbon will build up in atmosphere, it change the climate. So from economic point of view, sooner or later there will be losses in the GDP due to carbon emission. And also, not just losses, but also at the same time, you need mitigation. So you need investment into productivity to overcome these losses in the GDP. So practically, we can say that somehow we can calculate the present value of all this, both the losses and also the mitigation investments. And the present value will be the social cost of carbon, but this can change in time. So the DICE model is quite forward-looking. So yesterday when I started to write and when I started to play with the model and so on, I was able to say, or I was shocked at the first time, that practically it tries to forecast for the next 500 years. So we can say that, yes, ambitious, but that's why we can see long-run influence of the different policy decisions and different parameters. So that's why I can say it's reasonable. Just for me, it's really strange that what kind of time scale are we using here. And also, the macroeconomic part is, let's say, quite simple. So this is not the part what they are focusing on right now. So mostly they are trying to emulate GDP. And there is a labor component, there is a capital component of the GDP, and practically they are just analyzing that what eats away the GDP and what replicates the GDP and how can you recover from these issues. And also there is the carbon tax component. So what will happen with the carbon pricing in time if it changes as well? So most of the model is absolutely not dealing with macroeconomics. It's much more like focusing on carbon emission, carbon cycle, climate change. So it's a really strange interaction between macroeconomics and climate analysis. But still, we can say that right now, the key paper and the key model, which is widely used, is published by, or it was written by Nordhaus, and he's an economist and he got a Nobel Prize as an economist, so that's why we can say that we are still talking about economics here, not completely natural sciences, but it's somewhere between social sciences and natural sciences. So, and it's also really interesting because to calibrate this model, they are using or highly utilizing results and publications from natural sciences. So how can you define carbon cycles? I will try to show you some alternate models which were also built into the DICE model, or they are also DICE model derivatives, because practically this is not the work for an economist, but his work for an economist is the force factor, and we can talk about the economic damages. And if you would like to build up something like this, then still this is a framework. So sooner or later, it will be integrated into the DSGE environment. And last year, when this class was kept by someone from the Hungarian National Bank, they were saying that now Oxford University has their
model which integrated DICE into the DSGE, just you have to pay a lot of money for that. So we are talking about millions of forints. So at least the DICE is free. So you can download the code, and I will show you some demonstrations with MATLAB. Unfortunately, this MATLAB on this computer is dead, so we cannot run it, but I saved results on my computer. So practically what we can say here, that they are taking a neoclassical optimal growth model, the Ramsey model, and then they just add this loss function to it. So they can say that, okay, let's include time investments, and it will still used as a capital investment. And also, what they are trying to do here is to optimize social welfare function. So there is a B component, so this is the instantaneous social welfare function, which is related to capital consumption, per capita consumption, population, and also there is a discount factor. But in the case of population, it's also pretty strange that it allows the population to grow until some level for the next, if I remember well, 200 years or something like this, and then there is a plateau, and after that it's fixed. So also we can say that, but we can modify it. So if someone would like to say that, okay, but let's add aging to the game, then you just have to dig down in the code, because the entire DICE model has only 4 functions in MATLAB. And practically you just have to look for the block where they are writing about population generation, and if you are parameterizing it differently or you are replacing it with your own equation, then it starts to behave according to this. So it's really funny. And also, obviously, there is another arbitrary function, the discount ratio. So how can you calculate the present value of all the future losses and investments related to climate change? So, yeah, this will be tweaked as well sometimes. Okay, if we are talking about the utility function, because one side of the equation is the welfare function, the other is the utility function, which uses completely the same variables, just this one is about utility, then we can say that this will react on the variable called capital consumption. So we can say that this is only parameterized consumption here, and also we can parameterize But at the end of the day, the strange thing is that, okay, we have this W here, and this is one of the most important things to optimize, but at the level of equations, this is not appearing again. So we can say that at the beginning we are defining that, okay, we are focusing on these things, but as you will be able to see, it's just there at the beginning, and after that we will be focusing much more on this component here. So how can we define the net output? So practically the net output is the difference between the gross output, so the GDP, minus all the damages and mitigation costs. And that's why we can say that, okay, this is the Q here, but there will be the loss function, and also there will be the mitigation function here, and this is the GDP what is generated. So practically the economy will be forced, at least from this frame, the economy is forced to be grow way faster than it's supposed to be without climate change, because otherwise the GDP would be reduced to 0 So, yeah. And it's also, it's a really, so if you are looking on this equation, it's quite interesting that other schools in economics, the green economics schools, are saying that, oh, we don't need growth, at least growth should be limited to maintain things sustainable. While here we can see that, no, if growth is not there, then practically the GDP will decrease continuously, and then I don't know what will happen, but we don't want to try this one. So that's why this is, I think it's much more realistic, at least to maintain standard of living and consumption. Okay, so the gross output is a usual Klopp-Douglas function with capital, labor, and technology. And it's quite non-visible or non-transparent, so they are not caring about that much. It's just saying that, okay, let's use this GDP generation process. What is interesting that how they are trying to parametricize this. So Nordhaus was saying that, okay, let's take past data. So what can be expected? So in the past it was 2.2% per year on global level. So the base, or the most simplest model, the DICE, is focusing on the global economy, but also there were regional implementations of it, at least for the big regions. And if I was able to understand it well, they were just changing the population and growth parameters. So the natural parameters were the same because they are already happy to model this on macro level or on global level, not just regional level. It could be using completely different parameterization for that one. And also, they were taking data from the IMF forecasts, and we can see that, okay, GDP growth can be smaller in the far future, so that was necessary for calibration. And also population data is coming from the United Nations. We can see that for the next 100 years, population is growing, and they are estimating stagnating population because who knows what. So that's why it was quite impossible to generate further population data. Or they were saying that, okay, if someone would like to refine it, then you can build your own model and to include it to DICE. CO2 emission, there is an information analysis center for that, so they were taking the data from there and just utilizing it. And yeah, this no CO2 radiative forcing, so this is this term of forcing appears so many times in the different papers. So practically this is the carbon flow between the different agents. So how land emission, ocean, upper level of the ocean and deeper level of ocean interacts with each other to release and absorb CO2, and also what happens in the atmosphere and how things are interacting between them. So it was also coming from this IPCC 5 assessment. So this is the 5th assessment. This is the key document which describes climate change. So it's updated regularly. If I remember well, every 5 years or something like this. So it's quite reliable data. Okay, and the damage function. So omega, we can see that they are using quite a simplified solution. So they are saying that, okay, there is a V and it changes in time, but at the end of the day, we can say that this is a function just about the temperature change. So if the temperature changes, so let's say it increases by 1, then there will be some parameter here which describes the relationship between GDP loss and temperature increase. And also we can see that it's also on squares. So this is the asymmetric approach. In many cases, for example, when you would like to analyze inflation's influence on on the interest rate. Then you are just writing up the Taylor rule, but also you are adding the inflation on squares. Or if you are saying that, okay, which one is stronger, the inflation or the output, or the GDP change on the interest rate. So are using in one equation, inflation will be on squares as well, but you are running a second model with GDP also on squares. And you can see how the model reacts on it. This is quite the same thing because even if you can say that maybe temperature is changing, and it can change sometimes in a negative direction. But here we can see that this is in the loss function, it's on square, so it will be always positive. So this is how you can ensure that whatever shock is happening, it will be, the magnitude will be bigger, and it will go always positive. So, because maybe you were adapting your, let's say agriculture was adapting to higher temperatures, and suddenly there is a cold wave. So, also not that big. So, let's say, I cannot say it's volatility, but behaves like volatility. Yeah. And the other thing is the abatement cost function, so this is the mitigation. I don't know why abatement is used, mitigation would be much better term, but okay, stick to it. Then, this is where CO2 emissions are starting to happen, and oh my. So, CO2 emission, on one hand, it's quite simple because we can say that, oh, uncontrolled emission minus emissions reduction rate and exogenous land use emissions. So, this is what we are not able to influence. How was I able to?
Swiping, I think.
Yes, somehow I was able to. Just I was not able to feel it, so maybe. Yeah. So this is what we are not able to manage. This is emission reduction rate, and it's really interesting because practically the article says that the necessary necessary CO2 emission to produce one GDP is already decreasing. So even before climate change as a topic started to emerge in the literature and our ability to assess the CO2 emission effect, because maybe we were reaching some kind of development at the level of productivity, also at the level of service-based society from an industrial society. So maybe carbon dioxide output carbon dioxide emission to output ratio is now, it's already negative. So we can say that, okay, this is stuff what is happening, but also there is a volatility related to it. So volatility, we are in a different class. So this is the level of carbon intensity and the growth. But of course we can say that, yeah, but we can be much more aggressive here at the reduction rate. So maybe it's not just, we can force it out. Not just saying that, oh, productivity increase and then structural changes in the economy, maybe they can contribute to that we will emit less CO2, but we can say that, yes, but if we are putting carbon tax on emission and then we are using this money up to reduce practically CO2 in the atmosphere by some technologies, so maybe we can just take it out from the atmosphere and pump it in the ground and keep it there. So we are maybe using some previous depleted natural gas mines for this. So we are using geology up, or maybe we are just using electricity to split CO2, which would use a lot of electricity, but still we can do it to create carbon and oxygen. So if we are doing some geoengineering, then also we can have an influence on this. And also, if we are talking about geoengineering, then there are these geophysical equations. And here we can see that, so what is happening with the greenhouse gas emissions? Partially, they will come from this equation. So this is what humans were generating. And the second part is the atmospheric, the upper ocean, and the lower ocean interaction. So, because lower oceans can also absorb, and any liquid absorbs gases. So, this is their behavior. Just changes in the temperature of the liquid can have an influence on the ability to absorb gaseous materials. Also, because of lower oceans, there is a pressure on it. And we know that also if you are buying a Coke or carbonated water, we know that under bigger pressure, the gas remains in the liquid, but once we are releasing the pressure, then it goes back to gaseous state. This is the same thing, so if maybe ocean currents are changing, then more CO2 can come up, so that's why we don't want to mess this thing up so much. But they are able to build into the model because we have some kind of reliable measurements at this level, or at least estimations. So, if we are going forward, then there is this accumulations and increased radiative forcing. So, how these things are moving here and there. So, all this production part, then storage part will be put here to describe the wandering of these things. And at the end of the day, this is how they can use all these forcing equations are used to define the temperature increase or decrease. So this was the state in the afternoon when it was blowing my mind, and I started to edit the videos for yesterday's seminar because yeah, it's nice, just yeah. And we can see that, okay, we have a global mean surface temperature, and also we have a temperature for the deep oceans, which can have also a feedback. Practically, if people, when they are talking about two-step models, they are always referring on this thing. So how can you define temperatures in the atmosphere and also in other places? Because to estimate temperature change, you have to solve all these steps before. So this equation, that one, and at the end you have this. And also the ugly thing is that you will need also parameters for that. So why? So how important is this forcing function? For the forcing function, you need this parameter to define that, okay, but the emission is how it's happening. And also for the emission part, you need to parameterize this thing. So it's really lots of regressions to define empirically these parameters. Yeah. Okay, but so this was the Nordhaus version of for the DICE model, but this Geoffroy article was referred so many times that I wanted to include it, somehow include the presentation, and I tried so much, so maybe I spent nearly an hour to define or to add further equations until I realized that so the problem is that Nordhaus provided a really streamlined and really elegant way of defining the equations, while this paper was not that nice, but at least I was not able to conduct them because the description and the notations and everything was quite different. But in the appendix, I was able to find a really strange description, but practically quite efficient description of their own two-layer energy balance model because they were defining it as an electric circuit, which is strange, but okay, so we can see that this is the temperature equation, so this is the equilibrium temperature. And this is going up, and there is a resistant part due to radiation. So some part of the temperature obviously irradiated away to the space. So this is not a problem for us. But what remains there, it can go also through a resistance, and this is the surface temperature, surface air temperature, because it's boiling up. And also there are capacitors built in. So the capacitor, in this case, it can be all the oceans, rocks, and everything which can be heated up. Otherwise, the air would heat up. So, yeah. But this is the one-layer model because the two-layer model. So that's why they were able to say that not just rocks and stuff is heating up, but also deep ocean heat uptake flows can be affected. Just, yeah. Okay, so we can see that after that they were building up fancy equations based on this. But let's go back to economics. So we can see that now we have this fancy welfare function here, and still we can say that okay, but some components are still not defined. So first of all, we have this discount rate, which we can see is related to the generational discount rate on welfare. So how much money do we want to put in to maximize this thing, or maybe there is the generational discount rate, so because we don't care about this. And also there is the inequality aversion, there is another key parameter. So how can we deal with this one? And first, there is a welfare discount rate, and it's not observed in the market, so it's people have this, but we cannot define it how. But there is this goods discount rate, so practically we can see that this is the amount of stuff, goods and services which were produced in the economy. And so this is the real return on investments. Practically this is assumed to be 4.25% per year during the period until 2100, because this is the historical average. So they are taking that, okay, maybe we would like to maintain the same real return on investment. And also you can see real return. So still we are not talking about inflation. Inflation is completely not a part of this process. This is without any kind of monetary things. At least we have some discount rates, so we can see that interest rates are already there, because otherwise we are not able to work with the main equation at all. But also on the other hand, still we can say that it's far from perfect. So we have this, and also the rate should reflect actual economic outcomes. So savings rates and rate of return on capital can change in time. So they will create this as a dynamic variable. And as a result, they are creating this equation. So there is the growth rate is always eating up the discount rate, and also at the same time this inequality aversion is also related to the growth rate, and there is the social time preference ratio. So practically the relationship between growth and the discount will be defined by the other factors.
Professor,
yes?
T here refer to time or temperature?
T in brackets, it's always time. So we have estimations for each years as time goes ahead. If it's a big T, then that's the temperature.
But the big T is in Celsius or Kelvin?
That's a great question. When we will check the results, then we will see it, because I know that in the documentation there was. Yeah, I was also thinking about it. Maybe it's supposed to be Celsius, because it's much easier for calculations. But yeah, yeah. Yeah, but practically Kelvin is the same like Celsius, just we are defining the zero at different levels. Yeah. It's not Fahrenheit, at least. Yeah. I don't know why they are using it, but okay.
Because it's cold.
Yes. Okay, so at the end of the day we are able to reach our objective, because before we are forgetting it, so the objective is to define the SCC, so this is the appropriate tax ratio on carbon emission, because if the tax ratio on carbon emission is the same like the social costs, which are calculated as a present value, then we can mitigate all the losses and we can deal with it. If the tax ratio is way lower than the SCC, then it means that we are in a sustainable path. And practically they are saying that, oh, it's no problem. So if we are taking the SCC and we are taking the derivative of the consumption and divide it with the emissions, and both of them, so they are derivations. It's not just that, but we need to derive both equations, and then we can get the SCC at the end of the day. And then we can have fancy results. So first of all, yes, it's in Celsius. So first of all, we can see that industrial CO2 emissions can be estimated for the next 100 years by the following ways. So these are the different models, and we can see that there were previous DICE models, but Nordhaus says that it was not that precise, or it was even more sloppier than what we were able to see today, because they have to develop it. So right now this is the most up-to-date version of the DICE model, and we can say that it's a bit more optimistic. So industrial CO2 emission will be a bit smaller. Just the problem is that this amount is produced and added to the atmosphere every year. So this one, and this. So it's still growing. we are not able to say that, oh, it's growing until 2100, and maybe after that declining, but still we are adding each line to the atmosphere again and again. So if you would like to reduce CO2 in the atmosphere, it should go downwards. So we can say that, oh, this is an optimistic scenario. No, this would be an optimistic scenario, because in this case we are doing something. In this scenario, at least, yeah, it's a marginal increase. Yeah. So, temperature increase. This is not so great. So if we are looking on the data, 5 or 4 Celsius, so whatever we are taking, it's still terrible. So, and after that, they were providing us different parameters with different alternate discount rates, and I don't know why I did not add it, but these are supposed to be the social costs, so optimal rates. And also we can see that if we are using different discount rates, the social costs on carbon can be quite different. So the DICE starts here, the other model starts here, but we can see that the discount rate should be around 2 point something, 2.5 and more, and the social cost in this case it will be lower, but this is the starting point, so it will just increase further and further from this level. And also, since they were adding some regional description that how social costs can be changing with each CO2 emissions, we can see that EU and the United States is supposed to have way bigger, China even way bigger, but there are regional differences. Unfortunately, the article did not write so much about this. It was estimated, but okay. But after that, I was able to see that this Pindyck approach was also used and cited in so many different ways, and also it's quite popular to integrate into DICE model. So at least the basic concepts I would like to introduce you, because here we can say that it's less ambitious, so it's just focusing for the next 50 years, not 500 years ahead. And it says that, okay, there can be possible reductions in the GDP, and practically this is what we would like to avoid. So there is start point GDP, and then this loss function starts to eat this up, so you are forced to grow faster again. And this is the problem. So we don't know the probability of loss. So because we don't care if the climate change has a small or minor influence on the GDP, because it always had. It's no problem for us. But if there are catastrophic situations which are, let's say, removing 20% of the GDP, then this is relevant, highly relevant. So practically what the added value of this approach is that they are focusing on the distribution of the unwanted events. He tries to model the influence of different distributions, so not just normal distribution, but factor distributions also on the GDP, in the case of losses. And practically it says that we have to look for the tails of the distribution. So, because also from risk management it's quite important that all the crisis situations are always happening on the tails of the probability distribution, because this is where we can find the huge, well, the events with the biggest influence and also with the lowest probability. So practically, the added value of any climate-related action is that we can eliminate these fat tails from the equation. So it means that if we are able to discount the tail, which was cut off, so the truncated distribution, then we can also estimate this social cost much more efficiently. So, yeah, in this case, you just need a distribution and a loss function z here, and after that, you can start to build up this model. And sooner or later, so assume that the percentage reduction in GDP z varies over time as it follows. So we have nice E, and it can be familiar. So if we are thinking about continuous interest rates when we are discounting things, It's always the same, just without, except we don't have betas here. This is the R, the interest rate. So this is completely the same thing, same impression, just right now we would like to find the beta which describes the relationship between the loss functions in time, because this is in time t, this is in time m, so if we can find the relationship between them. And unfortunately, in this case, the t is not temperature, it's time. So this is an inconsistency again between two different papers. But yeah, okay, so he was assuming it that the beta can be 0.01, so it's 1%. After that, he was able to define how GDP evolves, how the losses in the GDP are evolving. We can see that the same thing, just the one minus is working here and there, because this is the loss, and this is the growth part. And after that, what he did was quite interesting, because he wanted to test different distributions. So practically he went to experts. So he conducted interviews and also compared different reports, and he tried to write or to estimate the appropriate distribution functions for climate-related losses, which is quite innovative on one hand, but it was, yeah, so it's strange. Because, okay, the loss function you can estimate on empirical data, but the mitigations program, you can just estimate it, that you should have to mitigate this one. But you have no idea how it will be done. Productivity, technology, something will happen, maybe, and then you can mitigate this. Or you are just using taxpayers' money to rebuild again and again with the same technology. So, yeah. And after that, he was able to define the present value of the avoided reductions in GDP. So this is when we were cutting off the fat tail of the loss function. And cost of the scenario is the total amount required emission reductions over some time horizon. So it still says that, okay, but to cut this thing down, to cut down the possible losses, we have to cut back emission as well. So that's why, to represent this trade-off, this is the average measure of the social climate cost. And this is what defines what should be the today's carbon tax and also futures carbon tax. So it's still again a dynamic tax, which can increase in time. And it's also quite robust. So it says that, okay, margin analysis would be really hard to model, so it starts with this approach. And after that, he puts all the data inside the equation, so we can see now we have a nice B and a nice delta emission, and then at the end of the day, we can have this equation. And if you are taking this equation and put it back to the DICE model, then we can have much more fancier results. And okay, in this case, I was saying that, okay, doesn't matter how can we write this thing up, they are behaving the same way, just you will see that it's not, because already you can remember that the DICE provided double-digit SECs, and we already see triple-digit SECs. So it says that it's absolutely not enough what they are using right now as carbon-related costs or taxes or something like this, because this is way not enough. To avoid fat tail situations, you need tax and spending at this level. So, yep, it was the first shock, but then let's see if we are using the simulation, then what will happen. So if you are clicking on this link, then you can download, so there is a GitHub link there, and then you can download the documentation and also all the MATLAB codes. So it's just 4 MATLAB files. Unfortunately, the MATLAB is not working right now here, so you can see the main code here. And practically this is not so many things what we have to optimize. So these are the user options. So time step, number of years, mostly I don't think so that we have to change this, and all the things what we can parametricize manually, these 3 parameters which defines climate model, carbon model, damage model, and the second thing is that how different constraints and savings rate are affected. It would be way harder to do so, and then the rest is just about computation. So mostly what we have to do here is to change some parameters here in these 9 lines if you want to do anything, and after that just Control A and hit F9 and then it will run. So it's quite straightforward and quite simple. So what I focus today is only the first 3 parameters because it was completely enough to dig it up. So first, in the climate model, we can use the DICE, or we can use this Geoffroy dynamics. As you can remember, that was the electric circuit thingy with the different feedback structures. Then carbon models, this says that this paper defines them. I checked them and I was not able to find where, but it was written somewhere. Just I was not able to identify why they were different and why they were significant, so I kept it in DICE. Damage model, we were able to see the damage model from this Pindyck with the tails, so you can use the DICE or this Pindyck as the expert settings, and that's all. Yes. Okay, parameters, I kept it them like before, so I did not want it to change anything because it was already interesting to see. So this is just DICE, the baseline model, and we can see that atmospheric temperature, what will happen, it will go up within 200 years by 4 Celsius, then sooner or later it starts to decrease, but it remains at 2 Celsius, the positive level, even 500 years later. And also we can see that carbon prices should increase at this level, and they will peaking around the next 200 years, then they can go down as the model runs out. And also the emission control rate, it should be increased for 1.5 or 1.5 century until they are able to do something to cool this thing down. And also you can see that atmospheric CO2 emission can peak earlier, before the temperature peaks as well. And to avoid further temperature increase, practically you need really aggressive ways to reduce carbon to emission, and sorry, not the emission, the concentration completely. So you have to take out carbon from the atmosphere. Is not enough just to cut back emission, but you need much more aggressive engineering solutions. And still we can say that even if you are cutting it back from the atmosphere, so we are way under the initial level, so we have to spend a lot on it, still the temperature will remain at higher level. So this is the messing up the situation, but we tweaked it case. And also we can say land emission, so it's nearly going down to 0. So practically we have 200 years to cut it back to 0, because if you are not cutting it back to 0, then this thing continues. So, yeah, optimistic future. And yes?
What is the benchmark for the temperatures? If we're saying that in 2015 it's going to be like 1 degree.
Yeah, so the base is 1900, so century ago, and that's the benchmark. Yeah, and to compare this, we are already at higher level, so that's why it's not starting at 0, but at the higher level. And if you are checking, okay, so the savings rate was the really smooth scale, so I was not able to enhance this. But if you are looking on labor force, so you can see that they are expecting the growth according to United Nations data until 2100, but after that they don't have information on expected data about it. Also, what is interesting that we can see the gross output and the net output with the losses, and practically we are looking on it that difference is not that much. Just you should not forget that we are talking about an entire planet. So maybe the difference is an entire country or more. So and also, yeah, investment is still increasing. Oops. And what is interesting here, why these two things are? Oh, okay. Just it should be the entire social cost of carbon. So we can see that the social cost of carbon and the spending on it should increase for nearly 400 years until it's reaching its peak, and then it can fall down. So we can say that, oh, at the beginning it will be cheap, so yes, it increases, but who cares? But the problem is that this is quite an optimistic scenario. So if we are using the other fancy ones, so I was using the updated Geoffroy dynamics and also the Pindyck avoiding fat-tailed GDP losses approach, then here we have a way more aggressive temperature change in the atmosphere, so we can see that, oh, it was, yeah, here, this is the scale, so it's increasing, then it falls down. And also the same thing is the atmospheric concentration, so it requires way more aggressive approach. And but practically we can say that land emission must be ended within 200 years. So this is not the shocking part, and this neither, because it's quite similar to the previous one, but this is. So here we can see the social cost of carbon. It comes forward in time. So now we can see that no, this should be increased in the near future. So within this century, this should have a way steeper trajectory, and go on and go on and go on. And also we can see the peak point. So it's 7,000. something, 7,000, and this is 2,000 and something. So not just the trajectory is different, but practically the amount of money what we are talking about, and this is US dollars per ton of CO2 and in 2010 US dollars. So, yep. So changing some parameters or equations can have a quite significant impact on how these models are behaving, and right now lots of research and development is made to integrate this DICE model into DSGE and also into central bank activities and lending regulations as